So in our last class we have discussed the subsequences, right? So what is subsequence? You know that basically you have some sequence xn, then you have another monotonically not monotonically strictly increasing subsequence of natural number, that is your Rn. If you have basically Rn is strictly increasing and belongs to natural number n, then you can say xRn is your subsequence. Okay, so this thing already we have discussed, and there are some example this type of thing we have done. And next we have done that if your main sequence xn converges to L, then your all the subsequence xRn will be converges to L. So I think this is our last class that we have discussed. Okay, now I am coming to the next theorem, that is your if you have two sequence. Okay, for example, one sequence is your x2n, another sequence x2n minus 1. If both sequence converging to your limit L, then you can say your xn is also converging to L. Okay, so if the subsequences x2n and x2n minus 1 of a sequence xn converge to L, then xn is convergent and its limit is also L. Okay, so this is, you have a theorem, you have to prove this. Okay, so if your x2n converging to L, so you know the definition, right? So let's write this. So for an epsilon greater than 0, there exists a k1 belongs to natural number n such that what happened for this one, that your x2n minus L less than epsilon for all n greater equal to k1. Okay, so similarly a k2 भी exist करेगा, right? K1 and K2 we can write directly as that this thing, and x2n minus 1 minus L less than epsilon for all n greater equal to K2, right? So this two thing you have. Now what you have to choose, you just take, you know how to find the intersecting region, right? So choose k equal to max of k1 comma k2. Okay, then there exists k then so basically this is the maximum. Then what happened, you can say, then we have basically u2n, this will be belongs to L plus epsilon and L minus epsilon, right? And your L minus epsilon, then u2n minus 1 less than L plus epsilon for all n greater equal to k, right? Now you see, you know, for n greater equal to k, your number will be either even or odd. So it will be either in this form or in this form. There are no other way, right? So obviously combining these two, you can say thus you can say L minus epsilon less than un less than L plus epsilon. But this thing we can say, but what should be the range of n? You see, this is whenever your n greater equal to k, so obviously from there you are getting 2n is actually greater than 2k, right? 2n greater equal to 2k, or and for this one what you have 2n minus 1, that will be 2k minus 1 type of thing, right? So combining these two, you have that this is valid for all n greater equal to 2k minus 1. Okay, because what is the range? If you consider that n greater equal to k, so the starting point will be 2k minus 1, right? And this will be from 2k, so obviously we have to take the minimum one, so that's why. So un will be lies in this range. So this implies that un, or you can write un minus L less than epsilon for all n greater equal to 2k minus 1. So un is convergent and limit un is your L. Okay, so this is your so this is your theorem. Now you have a homework 1. Okay, this is the same type of thing. So if u3n minus 1 and u3n minus 2 all are convergent to L, then proof and limit un is your L. Okay, this is your homework 1. Okay, okay, next you have the subsequential limit. Okay, what is subsequential limit? Like basically, if you a number L is said to be subsequential limit if there exists subsequent u Rn that converges to L. Okay, so let xn be a real sequence and a number L is said to be subsequential limit of xn if there exists a sequence xrn of xn that converges to L. Okay, example, if I say if your xn is your sine n pi by 4. Okay, so for this one you can have that 0 is a subsequential limit, right? We will say we will see 1 by root 2 also is subsequential limit. Okay, for example, what I have to consider, for example, if I consider x, I think 4k or x4n, you see that will be converging to your 0 number. Okay, this one I think maybe x8n plus 1. If you consider this thing, your that sequence will be converging to 1 by root 2. Okay, so how many possibility of subsequential limit here? So you will see here basically subsequential limit zero, 1 by root 2, minus 1 by root 2 and 0. I think these three are the all possible subsequential limit. Okay. Okay, fine. Next you have a important theorem, this theorem. A real number L is a subsequential limit of a sequence xn if and only if every neighborhood of L contains infinitely many points of the sequence xn. Okay, so basically a number is said to be subsequence limit if it for any neighborhood, okay, with contain infinitely many elements. For example, if I just consider the earlier example, right, sine infinity, how many elements in your main sequence? Obviously infinite, n is varies from 1 to infinity, right? So now we can say 0 will be subsequential limit if you consider a neighborhood around this 0, any neighborhood you will choose. So of the main sequence, this neighborhood contains infinitely many elements of the main sequence. For example, already we have discussed, right, that x4n, basically x4n is actually the exact element 0. So obviously, so how many element in your x4n? Obviously there are infinitely many, right? So that type of thing you have to so this is very important. Sometime this come in your I have seen in your previous year question. Okay, so obviously this is if and only if, so you have to prove both way. Okay, so first consider that L is a subsequential. So then this is very easy. Okay, so let L is a subsequential limit. Your L is a subsequential limit, obviously then there exists a subsequence xrn such that limit n tending to infinity xrn is your L, right? Because this is your subsequential, so obviously there exists some subsequence that converging to your number L. Okay, now choose, now consider for epsilon a equal element 0. Okay, now let us choose a positive, choose epsilon greater than 0. Okay, then there exists a k belongs to natural number such that what's happened, that xRn will be lies between L plus epsilon and L minus epsilon for all n greater or equal to k. Alright, so how many elements there? Infinitely many. Okay, therefore because this is for n equal to k, so k plus 1, k plus 2, in this way you can extend up to infinity, so infinitely many choice you have. So therefore L minus epsilon less than xn less than L plus epsilon for infinitely many values of n. So this is the thing, and you can choose your epsilon arbitrary, so that's why any neighborhood, that every neighborhood, that what is given. Okay, so since epsilon is arbitrary, so every every neighborhood of L contains infinite number of elements of the sequence okay. Next, conversely what you have, that conversely every neighborhood contains infinitely many elements, right? So you have to construct a subsequence that is converging to L, so in this way. So conversely you have every neighborhood of L contains infinitely many elements, right? So conversely, let you write that line, let every epsilon neighborhood L contains infinitely many elements of xn, right? So if every epsilon, so you just consider epsilon equal to 1, let epsilon equal to 1. So obviously for this one also then L minus 1 then less than xn less than L plus 1, right, for infinitely many of n. let S1 equal to n such that L minus 1 less than xn less than L plus 1. So what you are considering, what are the number for which your xn is lies between L minus 1 to L minus, you are collecting that set. Okay, for example, suppose your x3 in between this, so you can say then 3 belongs to S. If your x7 this is belongs to in this range, so then you will say 7 belongs to S. So in this way you are considering a S1. Now I think Somit sir had done the theorem that every subset of, obviously this is a subset of natural number, right? And you know every subset of natural number has a minimal element or minimum element. This is actually called well ordering property. So let that element is your R1. So by the well ordering property of n natural number, S1 has a least element. Say R1. Okay, so you have L minus 1 less than UR1 less than L plus 1. That's it. Now you change your epsilon. Let epsilon is equal to half. Okay, so same thing you have to consider this type of thing. Okay, then L minus half, L by half for infinitely many values of n. So let's consider S2 for which this is happening like that. So similar by well ordering property, there exists S2 has a least element R1, and we are consider this thing so that your this element R2 whatever it exists, that will be greater than R1. Okay, okay, because there are infinitely many choices, right? So obviously you will get some number R2 which is greater than R1. Okay, so in this way if you consider continue in this way, so obviously what you have, L minus half less than UR2 less than L plus half. Okay, continue in this way. You see here your this R2 this type of thing is actually increasing. You have a Rn sequence, right? That Rn is actually strictly increasing, like that we will consider. Okay, we obtain a strictly, so I think you got this point, right? Like epsilon equal to half you are getting, similarly epsilon equal to 1 by 3 you are getting similar as 3. In this way you are continuing in up to n and infinity. Okay, so you will get R1 R2 dot dot Rn strictly increasing sequence Rn such that L minus 1 by n less than URn less than L plus 1 by n. Now tell me, if you make your n tending to infinity, what you have? Obviously, or you can use your sandwich theorem also. If you make this thing, so obviously URn will go to L, right? Because this is also going to L and this is also going to L. So URn where they will go. obviously L. Okay. For n belongs to natural point, so you can use sandwich, no issue. Theorem: limit n tending to infinity u Rn is your L. That means you got a subsequence, right? URN that is going to L, so you can say L is your subsequential limit. Subsequence of UN so L is the subsequential limit. Okay. Okay, so after that we'll consider some problem. For example, your first problem: let u1, this is not related to previous theorem, this is problem from sequence overall. Okay, let un equal to √2. Okay, and u1, and suppose your un plus 1 is your √2un. Okay, so you have to prove that limit un will be 2. Okay, so how this sequence looks like: you see first element is √2. Can you say what will be the next element? So if you trying to find u2, you see 2 into u1, right? So that is basically √2. So this type of thing. What is the next element? 2 √2 right. In this way you have the next element. So in this way this element looks like. Okay, so the sequence looks like sequence is this type of form. Okay, now you see if you do un plus 1 square, what you will get? 2un, right? Okay, and if you have un square, what will get? 2un minus 1. So if you subtract un plus 1 square minus un square, you'll get 2 into un minus 1, right? So if you use a square minus b square formula, so you have un plus 1 minus un into un minus plus 1 plus un into 2 into un minus 1, right? Now you see whenever your element, obviously here you are saying every element is positive, right? So this element is always positive, no issue. Now if you suppose your u1 is your if your u1 and u2 relation is like this, suppose. Okay, what is the relation between u1 and u2? You can check in your calculator, right? So obviously here you can say you just find the value in calculator. Obviously you will get u2 is greater than u1. right? Now you see, if your u2 is greater than u1, okay, here this value, so from there you will get actually u3 greater than u2. Why? Basically, just in this relation you just put n equal to 2, okay, this relation. So what you will get, basically u3 minus u2, then you have u3 plus u2 equal to 2 u2 minus u1, right? This is you are getting for n equal to 2. Now you just think this element is always positive, this element is always positive, so from there you are getting u3 minus u2 is always positive, right? Because this element, if you do something by something, so this is element is positive. So if it is positive, so from there you can say positive means greater than 0, obviously, so u3 greater than u2, right? So in this way you will get u3 greater than u2. Similarly, now put n equal to 3, so you will get u4 greater than u3. So in this way you will get actually some increasing sequence, right? Strictly increasing sequence. I think this is clear. Yeah, the type of thing you don't have to write in your paper. Okay, so we know un is greater than 0 and u2 greater than u1, so this gives what they will provide: u1 less than u2 less than u3 dot dot dot. This gives un is a strictly increasing sequence. Okay, like that. Okay, now you see, if I consider in this way, and that again you have 2 un equal to un plus 1 square, right, from the first one. And you know un plus 1 square is actually because your un plus 1 is your greater than un, right? So this is greater than un square, you can say, because obviously this imply un plus 1 square greater than un square. So this if you use here, right, so you have this thing. So from there you are getting basically un square minus 2 un, this is less than 0, right? So you have, if you take common, so un into un minus 2, this is less than 0. So from there what you are getting, un, obviously you know un greater than 0, so this imply un minus 2 less than 0, as un greater than 0, so this imply un is less than 2. Okay, so what you are getting, you have a strictly monotone strictly increasing sequence, and that value is always less than 2. So what you have, you already have discussed the monotone convergence theorem, right? That if you have a monotonely increasing sequence and that is bounded below, okay, by some number, so then you have that is converging to the that is convergent and convergent to the least upper bound. So this is your actually, this 2 works as your least upper bound, so you can say that is convergent, right? Okay, so sorry, this is bounded above, sorry, not below. So un is bounded above by 2 and strictly or monotone, here strictly is more better, anyway, increasing sequence. So by monotone convergence theorem, convergence theorem. UN is convergent. So convergent, that is fine. So obviously let limit UN will be L. We don't know what is the number, because this is not, we cannot say this is the least upper bound, right? So if you have this type of thing, so you already have UN square equal to 2 UN, right? So if you make it limit n tending to infinity UN square, so what you have, L square equal to 2L, right? This imply L square, if you take one side, so you have this type of thing. And what this imply, basically L equal to 0 or 2, right? Obviously it will cannot be 0, right? Because all number is here greater than 0, so L cannot be 0. As your UN is greater than 0 and UN is strictly increasing. So what is your value? So L is 2. So in this way you have proved this. Okay, so your homework 2, homework 2 is your, suppose u1 is equal to root 7, okay, and un plus 1 is equal to root over 7 plus un. Prove that un is convergent to the positive root of x square minus x minus 7 equal to 0. Basically this equation have two roots, so you will see there is one positive root, and that or this UN is converging to the positive root of that one. So this is your homework 2. Okay, and you have one more homework. Okay, this is fine, you do up to this. In the next work we'll do this type of problem one more. Actually this type of problem is you will see in your previous paper. Okay, I am stop the lecture here. Next we have to finish the Bolzano stars and that Cauchy condensation. So I think 2 class is required to finish this sequence. Okay, bye for today.